Okay, so picture this. Berlin, maybe summer 2025. Temperatures are just soaring, breaking records, and the city's energy grids, they're really buckling under the strain.
Yeah, all those air conditioners running full blast.
Exactly. Millions of them just humming away, trying to keep homes even bearable.
Mm-hmm.
And maybe you're sitting there in your apartment just trying to catch your breath, and it kind of hits you. This isn't just some awful heat wave. It feels, well, it feels bigger, like an emblem of our whole situation right now.
Mm-hmm. These converging crises.
Right. We've got housing affordability problems, these extreme climate events, heat, floods, wildfires, and
Yeah.
this, growing inequality. It feels like our buildings, our homes, they're just fragile, kind of unprepared for what's coming.
It's a stark picture for sure.
But amidst all that, what's really fascinating and what we're diving into today is this solution. And it's not some like futuristic, untested thing. It's actually a refined concept. It's been around for decades, but it feels absolutely vital right now. The passive house.
It really is an incredible evolution in building science. And for this deep dive, our mission really is to unpack that. What exactly is a passive house? Why is it such a paradigm shift for sustainable living? And how does it actually tackle those core challenges you just laid out?
Okay.
So we're going to explore how they can, drastically cut greenhouse gas emissions, how they help us adapt to climate extremes, and create homes that are, frankly, as affordable to run as they are comfortable to live in. It's about building for tomorrow, but doing it today.
Right. Building for tomorrow today.
Ooh, I like that. So let's jump right in. What makes a passive house unique? And for me, it really starts with something we all want. Comfort. Real comfort.
Unmatched comfort, yeah.
Like comfort without compromise. Think about it. It's super airtight design. It just gets rid of drafts completely. So no more cold spots by the window or near the floor. Instead, you get this consistent, really pleasant temperature. Everywhere. In every room.
It sounds almost too good to be true, but that's the standard they aim for?
And that comfort, it's more than just temperature. You've got the heat recovery ventilation, the HRV system. It's constantly bringing in fresh filtered air, so your indoor air quality dramatically better.
Okay, so it's not stuffy, even though it's airtight.
Not at all. Plus, it blocks out a lot of outside noise. So you get this really serene, quiet indoor environment. And something that often gets missed, but is just as key for comfort. Humidity control.
Ah, right.
A well-designed passive house keeps indoor humidity roughly between 40 and 60%, which, prevents things like dry skin in winter or worse, mold and damp conditions. It's a whole comfort package designed right in.
That makes total sense. And all this seems to flow from the passive approach itself, the idea that these homes harness heat that's already there.
Exactly. They're designed to capture and use natural heat sources. Sunlight streaming in, the warmth from people's bodies, even the heat your fridge or TV gives off, it all contributes.
So you need way less energy for active heating and cooling.
Drastically less. It's about working with the physics, with nature, not just trying to overpower it with brute force heating or cooling.
Okay. And how do they actually achieve that? You mentioned the 5 building blocks.
Right, the 5 core principles. First up is super insulation. We're talking really high performance insulation in the walls, the roof, the floor. It minimizes heat transfer, heat getting out in winter or getting in during summer.
So like a really, really thick high-tech blanket for your house. You hear about R values and U values.
Exactly. R value measures resistance to heat flow. Higher R value, better insulation like a warmer blanket. U value is the opposite. It's the rate heat transfers through something. So for passive house, you want super high R values and super low U values. Minimum heat leakage.
Got it. Super warm blanket. Then second, and this sounds huge for comfort and efficiency, is airtightness. You said it stops drafts, prevents energy loss. How airtight are we talking?
We're talking incredibly airtight. They actually test it rigorously with something called a blower door test. The target is less than or equal to zero 0.6 air changes per hour, ACH at 50 pascals of pressure.
Okay, 0.6 ACH at 50 pascals.
Mm-hmm.
What does that mean in, real terms?
Think of it like this. If your house were a balloon, it would barely leak any air over an hour, even under pressure. It's exceptionally tight. That means no drafts, and the air you paid to heat or cool stays inside.
Wow, okay, that's tight. The balloon analogy helps. Third is thermal bridge-free design. What exactly is a thermal bridge? Sounds like something you don't want.
Definitely don't want them. They're basically weak spots or gaps in the insulation layer. Think of a concrete balcony slab that extends from inside to outside, or maybe a steel beam. These materials conduct heat really well.
So heat just flows right out through them.
Pretty much. They cause energy loss, create cold spots on your interior walls, and can even lead to condensation and mold because those surfaces get cold.
Right, so thermal bridge-free means...
It means designing to eliminate those pathways, using continuous layers of insulation wherever possible, and where you can't, like at window frames or balcony connections, using special thermally broken components. These have an insulating material built right into them to stop that heat flow.
Okay, so meticulous attention to detail, eliminating those weak links. And that brings us to number 4. High-performance windows and doors. These obviously aren't your standard double-glazed units.
Not at all. Typically, you're looking at triple glazing, so 3 panes of glass.
3 panes, wow.
Yeah. And the gaps between the panes are filled with inert gases like argon or krypton, which insulate better than air. Plus, they have special low emissivity or low E coatings on the glass surfaces.
Low E coatings, what do they do?
They reflect heat. So in winter, they reflect your indoor heat back inside. In summer, they reflect the sun's heat back outside. And they use warm edge spacer bars between the panes to minimize heat loss right at the edge of the glass. They're really highly engineered components.
Makes sense. If the walls are super insulated, the windows have to be too. Okay, and the 5th block. Since it's so airtight, how do you get fresh air? That's the heat recovery ventilation, right?
Yeah.
HRV or ERV.
Exactly. Vital in an airtight house. The HRV system continuously extracts stale, moist air from places like kitchens and bathrooms, and at the same time, it brings in fresh, filtered air from outside.
But doesn't bringing in outside air waste energy, especially in winter?
That's the heat recovery part. Inside the HRV unit, there's a heat exchanger. The warm, outgoing, stale air passes right next to the cold, incoming fresh air without mixing, and it transfers up to 90% of the heat from the outgoing air to the incoming air.
Wow, 90%. That's efficient.
Incredibly efficient. So you get constant fresh air, but you lose very little heat. An ERV, or energy recovery ventilator, does the same thing but also transfers moisture.
Okay, so ERV manages humidity too.
Right. Which is really useful in climates that are very dry or very humid. It helps keep that indoor humidity in the ideal comfort zone, that 40–60% range we talked about. So HRV or ERV, essential for air quality and energy efficiency in these buildings.
So these 5 principles work together to hit some really specific performance targets, don't they? You mentioned some numbers earlier.
Yes, the key metrics are very precise. For heating energy demand, the goal is less than or equal to 15 kilowatt hours per square meter per year. That's incredibly low.
15. Okay, and for total energy?
That's the primary energy demand. It includes heating, cooling, hot water, and all household electricity. That's capped at less than or equal to 60 kilowatt hours per square meter per year.
60 total. And the air tightness again.
That crucial air tightness target. Less than or equal to 0.6 air changes per hour at 50 pascals. These numbers aren't just guidelines, they're strict performance requirements for certification.
It's amazing how it all comes down to these measurable outcomes. And the whole concept, these numbers, they didn't just appear out of nowhere. There's an origin story here, right, in Germany.
There is, yeah. It goes back to 1991 in Darmstadt, Germany. A 4-unit residential building was constructed as basically a proof of concept.
The very first one.
The very first certified passive house. And it worked. It achieved that heating energy demand of less than 15 kilowatts per square meter per year. Its success was undeniable.
And that led to?
That success led directly to the founding of the Passive House Institute, the PHI, in Germany in 1996. They formalized the standard, the calculations, the certification process, and from that one building, it started to spread.
It really took off from there, didn't it? It wasn't just a German thing for long. It spread across Europe, Austria, Switzerland, Scandinavia were early adopters.
And then jumped the pond to North America, US, Canada, and even further into Asia, China, South Korea, parts of Africa too. It became this truly global movement.
Which is fascinating because climates are so different around the world. It shows it's not just a cold climate solution.
Absolutely not. That's one of its greatest strengths, adaptability. It's not a rigid, one-size-fits-all blueprint. The principles are universal, but the strategies get tailored to the local climate.
So, for instance, in really cold climates, like you see in Norway or parts of Canada.
There, the overwhelming focus is on maximizing heat retention. So super thick insulation, maybe using materials like wood fiber, which performs well in cold. Windows are absolutely top tier, triple or even quad glazed, minimizing any heat loss. You orient the building to capture winter sun.
Right, keep every bit of warmth in. And the opposite. Say, hot and arid climates like parts of the U.S. Southwest or the Middle East.
Completely different strategy. There, it's all about minimizing heat gain. You might use materials with high thermal mass, like concrete or adobe. They absorb heat during the hot day and release it slowly during the cooler night.
So the building kind of evens out the temperature swings.
Exactly. Plus, you need strategic shading overhangs, external blinds to keep direct sun off the walls and windows. Reflective surfaces, especially on the roof, help too, and generally less glazing, particularly on sun-facing sides.
Okay. What about hot and humid climates, like Southeast Asia, Singapore maybe? Humidity must be a huge factor there.
Huge! So, besides shading and reflective roofs, managing moisture is critical. This is where ERVs really shine because they actively dehumidify the incoming fresh air. Good cross-ventilation design helps too, sometimes incorporating tropical plants for shading and evaporative cooling effect.
So it's really about understanding the specific challenges of the climate. And for temperate or mixed climates, like Germany where it started, or maybe Virginia here in the US, places with both heating and cooling needs.
There, it's a balancing act. You need good insulation for winter, but also effective ways to prevent overheating in summer. So dynamic insulation strategies might come in, or adjustable shading that you can change seasonally. The window specifications are carefully optimized to balance winter solar gain with summer heat protection.
That adaptability is key. And the Passive House Institute itself recognizes this need for flexibility, right? With different certification levels, like Interfit for existing buildings.
Yes, Enerfit is crucial. Retrofitting an old building to full passive house standard can be really difficult, sometimes impossible without tearing it down. Enerfit sets slightly relaxed targets, acknowledging the constraints of working with an existing structure, but still aiming for massive energy savings.
What are the common things you do in an Interfit project?
Often, it involves adding a thick layer of insulation to the outside of the building, upgrading all the windows and doors to high-performance units, making the building much more airtight, and installing an HRV or ERV system.
And it works. You can get significant improvements.
Absolutely. There are fantastic examples like transforming a drafty 19th century row house in Brussels or renovating schools in Austria to near passive house levels. It proves you can bring older buildings way up to modern efficiency standards.
That's huge for dealing with our existing building stock. And then there are the plus and premium levels, too.
Right. Passive House Plus takes the standard passive house and adds renewable energy generation, usually solar panels. The requirement is to generate at least 60 kilowatt hours per square meter of building floor area per year.
So it starts generating some of its own power.
Exactly. And Passive House Premium goes even further. It requires generating at least 120 kilowatt hours per square meter per year from renewables. These buildings actually produce a significant energy surplus over the year, great for projects that have the space and budget for larger renewable energy systems.
So with all these levels, why should someone, say a homeowner, really care about getting the actual certification? What's the payoff?
It's about guaranteed performance. That certification is proof the building meets those strict targets. We're talking up to 90% less energy needed for heating and cooling compared to a standard new build. That translates directly into much, much lower utility bills, year after year.
Okay, the savings are obviously huge.
Beyond savings, it's the guaranteed comfort, stable temperatures, no drafts, quiet. It's the superior indoor air quality from the constant filtered fresh air. And something becoming increasingly important, it demonstrably increases the home's resale value. Studies show certified passive houses can command a premium, maybe up to 10% higher.
So it's a mark of quality that the market recognizes.
Absolutely. It signals quality, durability, comfort, and long-term affordability. When you think about the total cost of owning a home, not just the purchase price, but decades of energy bills, passive houses really redefine affordability. Maybe a slightly higher upfront cost, but the lifetime savings can be enormous. It flips the script from the house being an energy drain to being, well, almost a financial asset in terms of saved costs.
Okay, so we've got the what and the why. Let's shift to building smarter. The innovations making this easier and maybe overcoming some barriers. One barrier I've heard mentioned is knowledge fragmentation. Like the architects, engineers, builders, policymakers aren't always on the same page.
That's been a real challenge historically. Information tends to live in silos. The architect designs it, the engineer specs it, the builder builds it, the policymaker regulates it, but they don't always speak the same language or have access to the same detailed know-how needed for passive house precision.
So we need what, like a common blueprint?
Exactly. A comprehensive, actionable blueprint, if you will. Something that bridges that gap between design intent and on-site execution. It needs to empower everyone involved.
How does that work in practice? For builders, for instance.
For builders, it means clear, detailed construction guides, maybe visual manuals, hands-on training programs to build the necessary skills. It's a different way of building, needing more precision. For policymakers, this kind of integrated knowledge provides the data they need, the economic benefits, the carbon savings, to create effective incentives in support of regulations. It's about creating a shared understanding and a clear path forward.
And technology must be playing a huge role in bridging these gaps now. Digital transformation.
Oh, absolutely. Technology is a game changer here. Take AI-driven energy modeling. Designing a passive house involves balancing many variables: insulation levels, window sizes, orientation, shading. AI tools can now analyze thousands of combinations incredibly quickly, helping designers find the optimal, most cost-effective solutions almost in real time.
Making the design process faster and more accurate.
Way faster. And then there's building information modeling, or BIM. This is huge for collaboration.
BIM. Explain that a bit more.
Think of it as a detailed 3D digital model of the entire building that contains all the information, not just the geometry, but the specific materials, the performance data, the HVAC system routes, everything. Everyone, architect, engineer, builder, plumber, electrician, works off the same shared model.
So everyone sees the same plan, literally.
Exactly. You can catch clashes like a pipe trying to go through a beam in the model before it happens on site. It allows for real-time updates, shared visualizations. It dramatically improves coordination and reduces errors.
And we're even seeing things like 3D printing moving into this space, not just for models, but actual building components.
Yes, it's starting to happen. For things like complex wall systems with integrated insulation channels or custom shape components needed to eliminate a tricky thermal bridge, it offers precision that can be hard to achieve manually.
And for checking the quality on site.
Technology helps there too. Automated quality assurance. Think AI-enhanced blower door tests that analyze leakage patterns, or using thermal imaging cameras mounted on drones to quickly scan the entire building envelope for insulation gaps or thermal bridges after construction. It's like giving the quality controller superpowers.
X-ray vision for the building envelope.
Pretty much. And all this digital tech feeds perfectly into another major trend: prefabrication and modular construction.
Right, building parts at a factory instead of all on site.
Exactly. Manufacturing, building components, walls, floor cassettes, roof sections, even entire room modules in a controlled factory environment.
What are the big advantages there? Seems like quality control would be easier.
Huge advantages. Quality and precision are much easier to control in a factory setting, crucial for things like airtightness and insulation continuity. It drastically speeds up on-site construction time, less weather dependency. It significantly reduces construction waste. And potentially, as production scales up, it can lower costs through automation and bulk purchasing.
So faster, potentially cheaper, and higher quality control. Seems like a win-win.
It's a very promising direction for scaling up passive house construction. No more excuses about drafts because someone had a bad day on site.
Huh, right. And alongside these process changes, the materials themselves are getting better too.
Definitely. Advances in material science are constantly pushing the boundaries. We have things like vacuum-insulated panels or VIP.
Vacuum panels, like a thermos flask.
Kind of, yeah. They offer incredibly high R values and a very thin profile. Great for retrofits or anywhere space is tight. Then there are aerogels, super lightweight, highly insulating materials, also good for tricky spots.
What about materials that react to temperature?
You're probably thinking of phase change materials, or PCMs. These materials absorb heat when temperatures rise above a certain point and release it when they fall below. They can help stabilize indoor temperatures, reducing peaks and troughs, like built-in thermal buffering.
Interesting. And are there more sustainable options coming through?
Big push towards bio-based insulations. Things like cellulose from recycled paper, cork, hemp fiber, sheep's wool, they offer good performance, lock up carbon, and are much more sustainable than traditional foam insulations.
Good to hear. And windows keep getting smarter too.
Yeah, smart glass technology is evolving. Windows that can electronically tint to control glare and heat gain. And the low-E coatings we talked about are continually improving, becoming more selective, letting in visible light while blocking infrared heat even better.
So with all these innovations, better materials, better processes, let's revisit that affordability question. Is the perception changing? That passive houses are only for the wealthy?
It's still a common misconception, but we really need to look at the whole picture, the life cycle cost perspective. Yes, the upfront construction cost might be slightly higher, maybe 5 to 15% more, than a conventional code minimum build.
Okay, 5 to 15%. That's not insignificant.
It's not. But you have to weigh that against the operational savings. Remember that up to 90% reduction in heating and cooling energy over the lifespan of the mortgage, or even just 10, 15 years, those savings typically far outweigh the initial extra cost. The payback can be surprisingly quick.
Plus the higher resale value you mentioned.
Plus the higher resale value. And crucially, we're seeing more and more government incentives, tax credits, grants, low-interest loans. In the U.S., there are federal tax credits. In Europe, programs like the EU Green Deal and Germany's KfW Bank offer significant support. Canada has provincial and utility rebates. These incentives are specifically designed to bridge that upfront cost gap and make passive houses more accessible to everyone.
So the financial argument gets stronger all the time. Okay, let's think about where these buildings fit best. How do passive house principles translate to the urban environment? Cities seem like a place where they could have a massive impact, but also face unique challenges.
Absolutely. Cities have density, limited space, lots of older, inefficient buildings, but they're also hubs of innovation and policy action. Passive house principles are definitely being adapted for multifamily housing, apartment buildings, even high-rises.
How does that work differently? You've got shared walls, maybe shared systems.
Yeah, you have to consider things like sound transmission between units. The air tightness actually helps with that. Ventilation systems might be centralized or semi-centralized. Efficient use of space is paramount. But it's very doable. We see amazing examples like the Bonstadt district in Heidelberg, Germany, an entire city district built to the passive house standard.
Entire district, wow.
Yeah. Or look at Carmel Place in New York, modular micro apartments built off-site, achieving high energy efficiency even on a tiny footprint. It shows the flexibility for urban density.
And what about all the existing buildings in cities? That seems like the biggest piece of the puzzle. Retrofitting.
Huge potential there. That interfit standard is key. It allows cities to upgrade their older building stock incrementally without needing to demolish and rebuild everything, improving energy efficiency, comfort, and resilience piece by piece.
You mentioned the Energy Sprong initiative in the Netherlands earlier. That sounds like a really smart approach for large-scale urban retrofits.
It's incredibly innovative. They basically measure the existing building, then manufacture custom-fit, highly insulated facade panels and roof modules off-site in a factory. These panels often include new windows, doors, and ventilation ducts already integrated.
So it's like a pre-made wrap for the building.
Pretty much. Then they bring these components to the site and install them incredibly quickly, often in just days or a couple of weeks, with minimal disruption to the people living inside. It transforms the building's performance almost overnight to near net zero energy levels. It's a model being looked at globally now for rapid, deep retrofits.
That sounds incredibly efficient. And that brings us to the crucial issue of urban affordability and equity. How can passive houses help people who are struggling with costs, especially energy costs?
This is a really important aspect. Those dramatically lower operating costs directly combat energy poverty. When your heating and cooling bills are slashed by, say, 70, 80, 90%, that frees up a significant amount of household income, especially for lower-income families who spend a disproportionate amount on utilities.
So it's a social benefit as much as an environmental one.
Absolutely. We're also seeing community-led models emerge, like passive housing cooperatives, making these homes more accessible. And government support is often targeted here, subsidies and grants specifically for building affordable passive housing, or programs like the U.S. Weatherization Assistance Program, helping low-income households improve efficiency. Plus, tax credits for developers building affordable passive units.
So it can be a tool for social equity, not just environmental sustainability. And thinking bigger picture, how does all this connect to global climate goals, like the UN's Sustainable Development Goals, the SDGs?
There's a really strong alignment. Passive houses directly contribute to SDG 7, affordable and clean energy, by radically reducing energy demand, which makes it easier to meet remaining needs with renewables.
Makes sense. Lower demand is the first step.
Exactly. They strongly support SDG 11, sustainable cities and communities, by creating more resilient buildings, improving urban air quality, both indoor and outdoor, by reducing emissions, and tackling housing affordability.
And materials matter too, right?
Yes, under SDG 12, responsible consumption and production, the passive house approach encourages using low-carbon, sustainable materials, designing for durability and potential reuse, circular economy thinking, and minimizing construction waste.
And the big one, climate action.
SDG 13, climate action. By cutting operational carbon emissions from heating and cooling by up to 90%, passive houses make a direct, measurable, and significant contribution to mitigating climate change. It's one of the most impactful strategies we have in the building sector.
Okay, so we've covered the principles, the global picture, the innovations, the urban context. Let's get practical. For someone actually embarking on a passive house project, what are the key things to get right from the very beginning? It starts before you even dig a hole, right? With site selection and orientation.
Absolutely. The design process really begins with understanding the site. A thorough site analysis is critical. You need to look at sunlight patterns. Where does the sun fall at different times of day, different times of year? Use solar path apps, map the prevailing winds, understand the topography, any existing trees or buildings that provide shade or block wind.
So you really need to observe the site closely.
You do. This analysis then informs the building orientation. In cold climates, you generally want to maximize south-facing windows to capture free solar heat in winter, while minimizing windows on the north side where you get little sun but lots of heat loss. In hot climates, it might be the opposite, or focusing on shading those southwest windows. You also think about how wind flows across the site. Can you use it for natural ventilation? Or do you need to shelter the building from harsh winter winds?
Getting that initial positioning right sets you up for success. But even with a great design, things can go wrong during construction.
Hmm.
What are the most common pitfalls people need to watch out for on site? Where do projects typically stumble?
Where the best plans meet reality. Number one is probably still air leaks. Even with a good design, sloppy execution during construction. Poor sealing around windows, pipes, wires penetrating the air barrier can kill your airtightness target.
So constant vigilance is needed.
Yes. Interim blower door tests during construction, not just at the end, are a good idea. Using high-quality tapes and membranes and meticulous sealing of every single joint and penetration. Training the crew properly is key. Another big one is thermal bridges. The design might show continuous insulation, but on site, maybe a structural element is installed incorrectly, creating that pathway for heat loss.
So the builder needs to understand why it's designed that way.
Absolutely. And simple insulation caps. If insulation bats are compressed or cut poorly, leaving gaps, the performance drops dramatically. Precision installation, maybe staggering layers, and visual inspections are crucial.
What about windows and doors? You said they're critical components.
Improper window and door installation is a classic pitfall. Even the best passive house certified window won't perform if it's installed poorly, not sealed correctly into the airtight layer and the insulated layer. Using the right techniques and products is vital. Also, neglecting moisture control. In an airtight building, moisture needs to be managed carefully. Understanding vapor drive, using the right type of vapor barrier or retarder for your specific climate and wall assembly is critical to avoid condensation problems within the walls.
Sounds like a lot of technical details need careful coordination.
Which leads to another pitfall: poor communication between the different trades on site. The plumber needs to know where they can run pipes without puncturing the air barrier unnecessarily. The electrician needs planned routes, regular coordination meetings, clear plans showing service routes, and maybe having a dedicated quality control supervisor who understands the passive house details can prevent a lot of headaches.
And finally, not adapting the design.
Right. Ignoring climate-specific design. Trying to just replicate a design from a completely different climate zone without adjusting insulation levels, shading strategies, or window specs, that's a recipe for poor performance or discomfort. You have to design for your specific location.
It really underscores the need for precision and care throughout. Which brings us to quality assurance and testing. These aren't optional extras for passive house, are they?
No, they are fundamental. The air tightness test using the blower door is non-negotiable. It's the pass-fail exam for that crucial 0.6 ACH target. It tells you exactly how leaky or tight the building is.
And you mentioned thermal imaging.
Yes, so thermal imaging or thermography. Using an infrared camera, especially during or after construction, maybe combined with the blower door test, lets you literally see heat loss. You can pinpoint thermal bridges, find gaps in insulation, identify air leaks. It's an incredibly powerful diagnostic tool for ensuring the thermal envelope is performing as designed.
Seeing is believing, I guess.
It really helps visualize the invisible. And then, even after the building is finished and occupied, there is post-occupancy monitoring and evaluation, or POE.
POE, what does that involve?
It means continuing to track the building's actual performance, using sensors to monitor real energy consumption, indoor temperatures, humidity levels, maybe CO2 levels to check ventilation effectiveness. And crucially, gathering feedback from the occupants about their comfort and
So
experience.
you check if it's actually delivering on the promises.
Exactly. POE validates the design and construction, helps fine-tune system operations if needed, and provides invaluable data for improving future passive house projects. It closes the loop between design predictions and real-world results.
Wow. Okay. What an incredible journey through the world of passive house design. We've gone from the basic science and those 5 core principles:
Right, the super insulation, air tightness,
thermal bridge-free design, high-performance windows, and that vital HRV ERV system. Then we saw how it spread globally, adapting to all sorts of climates,
from icy Norway to humid Singapore.
and explored the really exciting innovations, the digital tools like AI and BIM, prefabrication, new materials that are making it more achievable, overcoming those barriers.